So this is section 3.1, conditions for the equilibrium of a particle. And what we want to be able to do is to be able to identify the criteria for a particle to be in equilibrium. So in this class, we'll be studying about particles that are in equilibrium. So consider a car that's sitting outside the building you're in. In this course, we'll consider this car to be a particle. And since it sits there without motion, we consider it to be in equilibrium. We can even be very specific and say that it's in static equilibrium. So as engineers, we need proof that it is indeed in equilibrium. To do this, we use Newton's first law, which requires that if all the forces acting on that particle, as engineers, we need proof that it is indeed in equilibrium. To do this, we use Newton's first law. Newton's first law. This law requires that all the forces acting on the particle should have a net zero effect on this particle. In other words, the sum of all the force vectors that acts on this particle should equal to 0. And that's given by equation 3-1. Now, let's see what happens if a car is traveling at constant velocity. Okay? In an ideal setting where there's no wind resistance, no rolling resistance, we would have sum of all the forces is equal to ma. However, this a can be rewritten as the change in velocity divided by the change in time. And since the car was moving at the constant velocity, the numerator is 0, the denominator has some value of time, but it still equals 0. Therefore, Newton's first law for equilibrium is still satisfied regardless of the fact that the car is traveling at a constant velocity. So let's draw the free body diagram of particle 2. So I have the ladder at an angle, and now I look at what type of forces act on that particle. So it would be the weight of the man standing on the ladder exerts a force onto the ladder. So that would be F of the man. And also there's the weight of the ladder itself that we have to take into consideration. So we'll assume that it acts at its CG, right? That's the symbol for the center of gravity, and it acts there. So we'll say that's the weight of the ladder. Because the ladder is leaning against the wall of the building will exert a force onto the ladder. So we'll say that's F sub B. And because the ladder is supported by the ground, it also will have this normal force. We assume that the ladder is not slipping, therefore friction comes into play. Therefore, there will be this friction force that resists the ladder from slipping. So that is a free body diagram of the particle 2, which is the ladder. So let's move on now to particle number 3, which is the man. So I have the man, and due to his weight, he experiences a force, F of the man. But the ladder actually supports him, and it exerts a force back onto him by the feet. So this is the force due to the ladder on the man. And that is a free body diagram of particle 3, which we consider to be the man. So we need to get some terminologies down. So some terminologies that you will come across in this course are called active forces and reactive forces, or reactions, right? Reactive forces. So in this diagram, what I've shown is, in these two diagrams, what I have shown are active forces in red and reactive forces in blue. Let's consider an example. Let's take a look at this. This is from section 3.2 of your textbook. It's example 3.1 on page 90. So what we want to be able to do is draw a free body diagram. So FBD stands for free body diagram for a particle that we're interested in, for a particle of interest. Now, there are multiple particles that we can analyze, so it just depends upon the problem statement. But for now, what we want to do is identify all those particles. So what are the particles that we see? Particle 1, I could have the eyelet at A. Particle 2, I could have the pulley wheel at B. Particle 3, I could have the rope at point C. I could also have the hook at point E. Oh, I'm sorry. I could have the hook at point D. Hook at D. Particle 5. I could have this ring at point E. And I could also analyze the sphere itself. And I could also analyze the spring. Right? So there are multiple particles that we can analyze. So let's just pick the sphere as a particle. So these are the steps you take. Step 1, you have to draw the particle of interest. Draw the particle of interest and nothing else. Step 2, identify the active and reactive forces. Then step 3, once you've identified them, what you want to do now is draw those forces as vectors. So draw force vectors. And if you know the magnitude and direction of them, you have to indicate it clearly on this diagram. So to draw the free body diagram of the sphere, we have the ground that's at an angle, and it will exert a force onto the sphere. So it'll be something like that. So we'll call that the normal force of the ground at, we'll just say normal force 1. And we also have the other angled ground, right? So we also have the other angled ground that'll exert a force onto the sphere, and it'll be perpendicular to that ground. So it looks like that, and we'll call that normal force 2. And we also have the pulley pulling up on the sphere. We'll call that force of the pulley or the cable. Okay, force of the cable. And we have the weight of the sphere itself acting downwards. Weight of the sphere. So that completes the free body diagram of the sphere.